And now you can see the full screen, right?
Yes, we can. Yeah.
Okay, perfect. Okay, also feel free to like interject in between or ask questions or anything. We can keep it very informal. Uh, okay, great. So, okay. Okay, so the recipe from GPT-1. So I'll give some motivation before getting into the my paper, but uh, because I think it's pretty important. So the recipe from GPT-1 to GPT-5 has been straightforward. That is, you spend more compute, you spend more data, and you get better models. And we have seen this in scaling laws and all of these papers that have come out. And this idea of scaling, which is like you spend more compute and more data, has pretty much existed for last 70 years in AI, like even before deep learning, interestingly. So this is like an analysis from Epoch AI, where they consider frontier models from 1950 to 2010. And if you see the frontier models from that regime, like we have been scaling compute of these frontier models since then, pretty much. And we have been doubling our training compute. So y-axis is the flops here. We have been doubling our training compute every year or so since then. What has changed since deep learning is the slope at which we are increasing compute has increased even more. So now we are scaling compute, like we are doubling compute every 6 months instead of every year. So we are outperforming Moore's law in a way. And in the deep learning area, we are not just scaling compute, we are also scaling data, because with deep learning you just need more data for all these models. So this is a trend where the y-axis is the number of tokens, and this is the deep learning era, and we're also scaling compute and data. But now I think a critical question is that will the same recipe that we have seen so far till GPT-5, will this recipe hold true from GPT-6 to GPT-N in the future? That is the recipe, which is that can we spend more compute, more data, and get better models? And this is a question mark. It's not clear. For instance, Elias Sutskever, he gave a recent talk at NeurIPS last year, and pretty much his whole talk that he gave at NeurIPS, his test time award talk, can be summarized with this one slide, where he said that pre-training, as we know, will end. Compute is growing, better hardware, better algorithms, larger cluster. But data is not growing. We have just one internet, which is the fossil fuel of AI. And there are a lot of research blogs that have actually gone in deep into this question of how big is the internet and all of this. And it turns out that we actually have a lot of internet data. So for instance, this is like about we have about like 1,000 trillion text tokens, we have a lot of image tokens and a lot of video tokens. But the issue is that even though we have so much data, the data is actually not growing at that fast pace. And a proxy metric to see this is by looking at Reddit data, for instance. So here is the amount of data that is being uploaded on Reddit on a monthly basis, and the blue curve is the actual trend, and the black curve that you see is exponential. And if you see until 2020, it seemed like we are exponentially increasing the amount of data, but since 2020 it seems to saturate, like the rate at which we are increasing the monthly data is saturating, so the second order derivative is not that high. And then you could ask, okay, why is data on the internet not growing? And there are many reasons behind this. I think the two most significant reasons is, firstly, the human population itself is saturating. So and because internet data is a cumulative knowledge of humans, human population is important, and it seems that we'll hit like max human population very soon. And the second is there's a lot of repeated data. So for instance, even if you think that you're uploading like we are uploading a lot of data on social media and all of these things, this data is still very repeated within itself. Like we are not really adding new information every time. And there is this pretty amazing paper that studies this idea of data growth more in a more statistical manner. So what they find is, for instance, this is a trend. So they try to project these historical trends in the future. So this is from 2020 to 2040. For instance, they're trying to extrapolate the historical trends. And this blue curve is the stock of internet data. So you see the internet data is increasing, but it's increasing at a slower slope. And this is the rate at which compute is increasing. Uh, okay, maybe it's fine now.
Okay. Okay, it's fine now.
Yeah, so okay, so this is the rate at which compute is increasing, this pink curve. Now you might wonder, okay, how are we plotting the pink curve here when the y-axis is the number of tokens? So what we do is we take the compute and we convert it into Chimchilla optimal and get the number of tokens using that, and then we plot it over here. So you see the pink curve is increasing at a much faster pace. And this is the blue curve is like the rate at which we are using data. So we are following pretty much the pink curve in terms of our data usage. And what they predict is like by 2028, their estimate is that this pink curve starts to match the blue curve, and you pretty much use most of the internet out there. And then if you go beyond 2028, then you have all this excess compute with you. uh, and you don't know what to do with all this compute, because our current scaling assumes that with this much compute you need this much amount of data. But when you have a lot more compute and not that much data, it's unclear how do you go forward and how do you keep the scaling trend going. So basically in this talk we'll investigate, can we trade off this excess compute with data somehow? Can we, and I think a central question here on is like, can we come up with sample efficient algorithms that can trade off compute with data to keep the scaling trend going? Because that's what we would expect. We'll have a lot more compute. And if you look at deep learning so far, primarily there have been like two algorithms that we have scaled historically. One is GPT-2 that was first introduced on text, uh, with this famous OpenAI paper. And the second is the diffusion objective, which was popularized on images by Berkeley folks. And both objectives are very similar. Uh, they both maximize the likelihood. The main difference is the way they factorize the joint distribution. And if you see the success of diffusion's initial success was on images and autoregressive success was on text. It has created both excitement and confusion in the field. For instance, we have started exploring diffusion on text to see how do these trade-offs hold on text. And then there are a lot of famous papers and very cool papers in this direction. For instance, D3PM was the first to introduce discrete diffusion on text. And then there are Gaussian-based diffusion methods like PLADE that also explore this idea. And then since then, there have been a lot of papers exploring diffusion on text. And similarly, in the vision community, we have started exploring autoregressive on images. So for instance, I'm not sure if you guys know, but the first Delhi paper was actually trying to do autoregressive on images, and they scaled it up. And then if you see the party paper from Google, which is also like a 22 billion parameter model, there was autoregressive in text to image generation. And similarly, there are a lot of papers now doing autoregressive on images. Now, in robotics, which is also a very exciting field, and like my advisor works a lot on this. In this, there are a lot of papers on autoregressive, and then there are a lot of papers on diffusion. So there's like a lack of understanding or lack of clarity as to like when do you train autoregressive or when do you train diffusion, because there's just so much plethora of papers in all these directions. So I'll just give a quick background on what is autoregressive and what is diffusion when I say here. So in standard autoregressive, what you do is you're trying to model this P of X of this whole sequence, and you're trying to factorize the data distribution in a left to right manner. Uh, in diffusion, what you're doing, so the diffusion was initially introduced on images, and the way it worked was you had an image, a clean image, and then you have a forward diffusion process and you have a reverse diffusion process. And in forward diffusion, you noise the distribution using Gaussian noise. And we have extended this idea to diffusion language models, which is now on text, which is also known as discrete diffusion, where instead of adding Gaussian noise, we randomly mask tokens out with different masking ratios. So that is the forward diffusion process. And we can compare like the training algorithms between these two regimes on autoregressive, let's say on text, and diffusion on text. So in autoregressive on text, you minimize this negative log likelihood of the data in a left to right order, and then you update the parameters and you repeat this until conversion. In diffusion LLMs, for instance, in MDLM, The way you do it is you sample the data point, you randomly sample a time step, which is your noising time step or noising strength. Then you mask using this noising time step, you mask the sequence, a randomly masked sequence, and then you have a like a reweighted version of like a negative log likelihood, which is also turns out to be the negative elbow, which is like an upper bound over the loss function, and you simply train. Um, and the way sampling works from autoregressive models. So this is the training that I covered, which is very similar for both. It's just in one you're randomly masking, and in the other you're training using left to right order. The way sampling works is in autoregressive, you just because you're training in a left to right order, you generate tokens in a left to right order, something like this. In diffusion language models, which is also you can think of it like a BERT like a model which is trained over random masking ratios. You just generate tokens in any order, like the way you see over here, and you can generate multiple tokens at once. And the way you compare between the way you can compare between diffusion and autoregressive is in autoregressive you're using negative log likelihood, and in diffusion you're using this elbow, and if you consider it as a loss function, then it becomes negative elbow, which is like an upper bound over the loss function. uh, so pretty much this covers like the rough background of diffusion language models versus autoregressive language models. But the issue is like if you see the results so far, like diffusion is still shows worse result on compared to autoregressive on text. So this is a result from the MDLM paper, and so there are like two conclusions to be made from this result. So here we are plotting the perplexity at different parameter count. So the first is that discrete diffusion seems to do better than continuous diffusion on text. So continuous diffusion is Gaussian noise, discrete diffusion is random masking. And the second conclusion is that autoregressive still achieves a lower negative log likelihood or lower perplexity than diffusion models. And there are works that have studied scaling laws for autoregressive models and diffusion models, and these scaling laws have found that diffusion, for instance, requires 16 times more compute to achieve the same negative log likelihood as autoregressive, or the same negative elbow, for instance. And but the issue with, like for instance, this paper studies this, but the issue is that, like for instance, these plots that you see, for
Quick question.
instance, yeah, sorry.
Sorry to interrupt. Sorry to interrupt. So, like, a quick question about the plot. Like, could you quickly explain like what the x-axis and y-axis is, just for the
The x-axis here is like the training flops used, and the y-axis is validation loss. So for autoregressive, it's your negative log likelihood, and for diffusion, it's your negative elbow.
Okay, so essentially what this plot is saying is, I guess, for a given validation perplexity or a given likelihood, like the likelihood numbers that you showed before, what this plot is showing is that diffusion requires 16x more compute, 16x more compute than the autoregressive models, right? If I'm not mistaken.
Yeah.
Okay, okay, cool. And then, okay, and the other way, okay, and the other thing is, the way you achieve this extra flops is by, you can take a small model and train it for longer, or you take a bigger model and train it for whatever amount of time so as to match, to achieve a desired number of flops, right? Okay.
Yeah, so exactly. So here in this plot, for instance, like the 16 time increase is not primarily by increasing the model size, it's also by increasing the data set size.
Okay,
So
yes. The training iterations where you have unique, assume that you always have unique data.
So because you're assuming in these plots, because you're assuming every token is unique, you're increasing, you're seeing more unique tokens, and also you're seeing more parameters.
Yes.
And as a result, you're seeing more compute.
Okay.
So,
cool.
I mean, there's some question in the chat, or maybe should I ignore this for now?
Yeah, maybe. Okay, okay. Is it the same slope? Yes, the slope is the same. I think it was by Quentin asked like if the slope is the same. Yes, the slope has been demonstrated to be the same empirically, but are the losses comparable if they use different loss functions? That's a good question. If you recall, like Mihir showed the slide, right? Like where in autoregressive model, you can compute the exact likelihood. That is, what is the likelihood of token 3 given token 1 and 2, token 4 given 1, 2, and 3, right? So yeah, the first row, as you can see, that is the exact likelihood. and it can be computed for the AR models, but for diffusion language models, you cannot do that. But what you can do is compute a conservative estimate on the likelihood. That is to say, you can compute an upper bound on the negative likelihood. Sure, these numbers aren't comparable, but this is the best we can do now. But we have a follow-up paper called esoteric language models where we compute the exact likelihood of diffusion models, but that's for later. Maybe we can happy to chat about this after the talk. But it is not ideal, but this is the best we can do now. Okay,
Yeah,
is a plot considering optimal data size and optimal hyperparameters? I think for scaling laws, um, we yeah, it's interesting. I mean, okay, when you study scaling laws, you are training models of different sizes. Naturally, every model size has some optimal parameter, a hyperparameter. But what I have seen personally in all these papers is that they pick a learning rate and stick to that learning rate. People have tried other methods to map learning rate to varying depths of the transformer by using something called a mop parameterization, but not every paper does that. I think Mihir can comment more on this because, he has done extensive work in this area. So Mihir, do you have any comments on how,
yeah.
like,
In general, like the goal with like the hope with this all these scaling laws is you're searching over a lot of hyperparameters, and then you're trying to fit a Pareto front over all of them. So if done well, the assumption is like you have tuned all the hyperparameters per model, and then you have achieved these scaling laws.
Okay, my only other question there would be like in your experiments, like maybe I guess like you'll be talking about it later, but did you do a grid search? Okay, so okay, maybe I'll let you. Okay, we'll answer this question later on in the talk. I just don't want to interrupt him. Okay, calculations are not comparable when looking at. Indeed, the calculation seems not comparable. Can you expand on what is NELBO? Uh, well, okay, NELBO. Okay, so there's a quantity called perplexity. A lower number means a better fit to the data, right? So in autoregressive models, perplexity perplexity is exponentiated not negative elbow. So lower perplexity means a better fit to the data distribution. In AR models, you compute the exact perplexity, but in diffusion, you'll compute a bound in the perplexity. Let's say the diffusion perplexity is the diffusion perplexity that you get is 27. Um, we What it means is your actual perplexity of the diffusion model is something less than 27. But nobody knows what is the gap? Is it 24? Is it 21? Nobody knows that. So yeah, it is unfortunate, but that is the best that we can do. But there are ways to compute the exact likelihood. Happy to talk about it after the talk. All right, Amir, I think I'll let you proceed now.
Yeah, sounds good. Uh, so okay, yeah. So the issue with the prior plot is like you conflate data and compute in a single plot, and it makes it unclear whether okay, do you need just more compute or you also need more data because these plots are in single epoch settings. So in this work, what we are essentially doing is we are disentangling data and compute, and therefore we study diffusion and autoregressive models in data constraint settings. So this is our work, diffusion beats autoregressive in data constraint setting. We'll also be presenting this at NeurIPS this year. And the motivation to pursue this project was something like this. So if you go back to the diffusion training objective, where you're doing randomly masking tokens and training the model to recover, which is something like this, like you could see that maybe there's a chance that left to right masking, which is like masking in a left to right order, could be included within diffusion training. Like there's a non-zero probability of you training in this order because you're doing random masking. Uh, and so the hypothesis was that okay, there is a non-zero probability of left to right masking being sampled in the forward diffusion process of diffusion training because you're doing all these random maskings. And then if there is a non-zero probability of such a masking being sampled, if you train the model for long enough with a large enough model size like the diffusion model, then it should at least be able to match autoregressive's performance if evaluated. And this was the hypothesis which we started the project. And therefore, we studied diffusion models in data constrained settings. We trained like 200 plus diffusion and AR models at different data set sizes and flop budgets. And pretty much this slide covers our findings. Uh, so in this graph that you see, the y-axis is validation loss, x-axis is the training flops, and the solid line that you see is the amount of flops needed for doing one epoch of training. And here we are studying on 100 million unique data points. And this each dot here represents a model that is being trained using the right learning rate so that you do the right thing at the certain number of epochs and using the specific learning rate schedule. So this blue curve is for autoregressive models, and each dot represents a autoregressive model that is being trained. And what you see here is a trend where after a certain number of flops, the validation loss seems to saturate. Uh, and this is
I have
yeah.
sorry, one very silly question. So every blue curve, right? Every blue point is essentially a model. Is it with like does it have a different? Is it of the same size or a different size?
So I'll come to in the
Oh,
next slide. I think I'll disentangle the flops into parameters and epochs. So
okay.
mainly the way we are increasing flops is by weighting the parameters and epochs. So we are studying along both of these axes. In this specific plot, I'm just showing over flops like combined between the two.
I see.
Uh, so the blue line represents the diffusion, and then the orange line represents blue line represents autoregressive, and orange line represents diffusion. And you find this interesting trend where there is like a point at which diffusion loss and autoregressive loss matches at a certain amount of compute, and then if you train beyond that compute or you spend more training compute, then diffusion starts to beat autoregressive. And we find this trend to hold not just at a specific unique data point but over multiple data points that we tried. So we tried 500 million, we tried 50 million, we tried 25 million, and at all of them we seem to find like there's this certain amount of flops after which diffusion starts to beat autoregressive in terms of validation loss. Uh, and we can then go into this question that Shubham asked, which is like, okay, how are we increasing the training flops? Because there are two ways of increasing training flops. One is you increase the model parameters, and the other is you increase the number of epochs during training. And here in this counter plot, like the x-axis that you see is the amount of training epochs, and the y-axis is the training parameters, and the blue is for autoregressive. And similarly, the right one is for diffusion. So the red is diffusion, blue is autoregressive. And there are some interesting things you can take away from this plot. So the first thing to take away would be that if you look at the one epoch loss, it looks like autoregressive seems to do better than diffusion at one epoch. So the validation loss for autoregressive is a lot better. Uh, and autoregressive achieves its best loss at about 50 epochs. And if you train beyond this, or if you train models that are bigger than this, you start seeing this overfitting behavior, which is represented by these light blue dots above that line, above that
Oh,
star. Yeah.
this is a very interesting plot. I have some questions here. So, okay, so you're doing multiple epoch training. So in each epoch, you have some finite number of unique tokens, right? Which is very unlike scaling laws where you assume where a token is never repeated, you sort of assume you have infinite data. Here, you restrict each epoch to have some number of unique tokens, right?
Yeah.
Okay. Okay, cool. And then what you observe is for the 144 million parameter model, as you train it, it achieves the best loss at 50th epoch. Okay. And when you train models with more number of epochs, it worsens the validation likelihood because of overfitting, I assume, right?
Yeah. Yeah.
Okay. Okay.
So for instance, like these
Hmm.
numbers, like 3.71, this number is exactly taken from this NeurIPS best paper, which is data constraint scaling laws. So they
33,
study
yeah.
so they study this at 100 million unique data points. So we try to match exactly. So we take a very strong baseline to ensure that there is a lot fair comparison. So this negative log likelihood numbers exactly match what they had found. Uh,
Hmm.
so yeah, basically autoregressive achieves its best loss at 50 epoch. And for instance, diffusion achieves its best loss at 500 epochs. Uh, and we try and we actually didn't see even signs of overfitting, because if you see, or out of all the models that we have tried, the best loss is achieved at the rightmost point in the line. Uh,
Yeah, and
and
this is very interesting as well, because when we wrote MDLM, we saw the similar behavior for LM1B, where we trained the model for a few days on one H100 node, and the model just kept on improving. And at one point, we just like gave up. I think the job died because of some reason, and then okay, we'll just like include the number at whatever number of tokens it was trained for. But yeah, I think when I saw this paper, I was really happy with the kind of analysis that went into approaching this observation, where on smaller data sets, people had seen like really good performance, or the gap between diffusion and AR being much smaller. But I think with this paper, you guys did a really good job. And the other question would be, okay, so what is the number of unique tokens? Could you remind me? I mean, I forget. Like for
so
this
this is
particular.
like this all these experiments are done with 100 million unique tokens.
Oh, 100 million unique tokens. Okay. Cool. Thanks.
Yeah, and so yeah, basically, mainly the conclusions are that diffusion achieves its best loss at 500 epochs, and then the best diffusion loss seems to beat the best autoregressive loss, which is 3.71 versus 3.51. And also the conclusion is like, because you're seeing more data, you also want to train on bigger parameter models, so the parameters are also more. If you notice, like the best diffusion loss is achieved at 416 million parameter model instead of the 144 million parameter model for autoregressive. um, and then because you're training all these experiments at different model sizes and different data size, you can go and fit scaling laws on this data. And this is like the standard scaling law equation from the Chinchilla paper and the neural scaling law paper, where n is the number of. This equation allows you to analytically predict the validation loss using fitted data points, and where n represents the number of parameters and the d represents the number of training tokens. So in this equation, you can give how many parameters you have, how many training tokens you have, and the equation will output the validation loss, let's say. And this a, b, e, alpha, beta are learned constants. You learn these constants by fitting to all the data points that you have trained. And in data constraint scaling laws, you generalize this idea, which is studied in this paper, where what you do is you change this n to n hat and you change d to d hat, and it becomes effective number of parameters versus effective number of training tokens. And then this d hat, which I showed you, is effective number of tokens. And basically, this ends up being like u is the amount of unique data that you're seeing. But every time you're doing an epoch, you're losing some value of the unique data. And that is equivalent to this 1 minus delta term. So every time you do an epoch, you lose some 1 minus delta term. And then depends on the number of epochs you're training, you can have like a total number of data that you're seeing as a result of training. And this 1 minus delta term is like in a way, it's like a learned constant, and it's specific to each model family. And you can analytically write this geometric progression into this equation, where the 1 minus delta term, which is the decay factor, becomes this term called RD star. And this is a learned constant. It's specific to each model family. And it's also called like the half-life of data reuse. So it's similar to like the half-life in physics, for instance, where after this much amount of time, you have lost the value almost half of what it was before. So in this, it means like after these many number of epochs, the value of your data is actually like lost by 67% of its time. So you have lost 60%, 67% of the data value after you have trained for that many epochs. And
Mihir, I have sorry to interrupt. Like, I think I have a follow-up question here, and it's okay if you don't have an answer. So, when I read Muninghoff's paper, they had this notion of effective number of tokens, right? Sorry, effective number of parameters. I guess you're going to talk about it later. So yeah, I mean, if you can just explain like what is the intuition behind that, because you have a model, let's say 110 million parameter. If you're doing multiple epoch training, why do you need to come up with this newer? Why does the effective parameters increase? Like, if you have an intuition there,
I
I know
mean,
it was
so
introduced in
can you
Muninghoff et al., but
of effective number of tokens, for instance?
sorry, what?
Do you get the intuition of effective number
Yes.
of tokens?
Yes, I
So,
mean, yeah. So the idea is that you have 100 million parameter, you have 100 million unique tokens for one epoch. The moment you retrain the model in the next epoch on the same set of tokens, it's not going to add similar amount of value as it would have had if those were unique, right? So
yeah.
yeah, the effective number of tokens part is clear to me.
Yeah, so like this effective number of parameters, so you can think of parameters as like a compression over the number of tokens in a way. So when you're increasing the number of tokens, you're also increasing the number of parameters. And let's say if your number of tokens is following a decay rate, okay, which is like once you're repeating, you're following certain amount of decay in in your tokens. And if you think of parameters as like compressed tokens, then you should also follow a decay rate on the way you're scaling parameters. So if you don't follow this decay rate, and if you just scale the parameters assuming every token is unique, then you will have a lot more parameters than data, and then you will become compute inoptimal. So that's why it's critical to introduce this idea of effective number of parameters to stay compute optimal with respect to your effective number of tokens.
Yeah, I mean, at some level, yes, I do get it. And like one final question, and we received a question on your previous plot, like the isolines. Do the isolines are equivalent compute, like in your previous scaling plot?
Which ones?
I think this one. Yeah. So yeah, my question would be like, like how do you get these isoline curves? Like, is it like you fit the equation that you just described? And
So by isoline, you mean like these lines? I mean, the way these lines are plotted is like it's based on when you have the same loss. So
okay. So
and
every point on that line corresponds to the same validation loss.
yeah,
Okay,
yeah, yeah,
cool.
exactly.
And
And
then,
yeah, yeah, go ahead.
sorry. Oh no,
No,
I was gonna ask my other question was how do you get these isoline curves? Because I imagine you train all these models. I mean, every point in this plot is a newly trained model, is a differently trained model, and you fit the equation that you showed us. You just showed us, and that should give you the isoline curves, right? If I'm not mistaken, or
no, so this is entirely empirical. So the way we have plotted this is like this has nothing to do with scaling law fits. So these lines that you see are just uh, entirely through empirical fitting within like a threshold of a value. If you have the same loss value, then you plot these lines.
oh,
Uh,
okay, but let's say let's pick a line. Let's say 4.32, right? Like the line 4.32. So why? Like I see it only goes through one, maybe 2 points. How did you? Why is the curvature the way it is that I
I
see
mean,
on the screen?
it is just a result like the empirical points that we fitted, like maybe like 2 points achieved the loss of 4.32, and they achieved, let's say, at a different parameter versus epoch ratio, for instance.
Okay, but
So
like, did you use a Python package for that? I mean, I'm just curious. Like, I mean, one could have
I mean,
also drawn a straight line through them, right? So.
uh, I think it's just like the way we have visualized in this is, I mean, you specifically mean in this plot, right? The ISO contour plot.
Yeah, yeah. So yeah, I mean, basically, let's say I have
I
all
mean,
these
it's
points.
more like you
Yeah,
can think of it like a 3D plot where the z dimension is the loss and
yeah,
the x
yeah.
and y axis is epochs and parameters. And now we have just drawn a line when you have like the same z value, for instance.
Okay.
If
In
I may,
that
So
I
I
think
mean,
Subham, if I may,
okay.
I think Subham is just asking what is the model class of this interpolation, right? And
Yeah,
it
yeah,
is like
exactly.
some
That's
default in a package, right?
yeah, yeah. So basically, like like for instance, you can fit a let's say given 3 points, you can fit a spline, you can fit a quadratic curve, you can fit a straight line. I was wondering if you yeah, like
I mean,
sorry.
uh, yeah, go ahead.
Oh no, yeah, I was just wondering, like, let's say you have all these points in 3D, and how would you go about, how did you go about fitting a surface to those curves? Like, uh, yeah, like, was it a quadratic? Was it quadratic, or was it cubic, or some linear interpolation thing? Do you
Yeah,
have any?
yeah, it's just like a linear interpolation between them. This was, I mean, there's not a lot of thought gone into this. It was mainly for just visualizing all these 3D points that
Okay,
we had from the top-down view.
okay, all right,
Uh,
all right, cool.
So the actual, like for fitting, we use like the standard scaling law equation where these values are more important, but
Okay.
these lines,
Okay.
these contour plot might not be that important.
Okay.
Uh, so yeah, so this ends up being your effective number of tokens, and this is your decay rate, and this is RD is the training epochs, and then your equation comes down to be something like this, where the RD star is equal to the half-life of data reuse. And then we fit this for diffusion models, this equation that you saw for diffusion models and autoregressive models. And pretty much you can look at the RD star. So we get like high enough R square. So we are, which means like we are able to explain high amount of variance in the data points for diffusion and autoregressive. And the RD star is like the interesting term to look at here, where what you find is that the diffusion RD star, like the amount of epochs you need for the half-life of data reuse is much higher than autoregressive, almost by an order of magnitude, which means like for diffusion, if you train under 500 epochs, it's 500 epochs is equivalent to losing, let's say, 67% of the value of data. But for autoregressive, it's something around 30 epochs. And then we do this data repeat experiment where what we do is we have a data. So we split it into different ratios. So with the whole data, we might train like a 5% with 5% of unique data, but for 20 epochs, and then 10% with 10 epochs, 50% with 2 epochs, and then 100% with 1 epoch, and 25% with 4 epochs. So we have, and the goal here is like we maintain the same number of flops across all these experiments. It's just the what's reducing is the amount of unique data that you're seeing while keeping the same flops. And then you can study this decay rate. So here each dot represents an empirical data point. And for autoregressive is in blue and diffusion is in red. And if you see, as you're reducing the amount of unique data fraction while keeping the same number of flops, you're seeing for diffusion it's similar to a flat line. Or the decay rate is very small as you're reducing the amount of unique data. But for autoregressive, on the other hand, which is the blue curve, the decay rate is much higher. And here, the fitted lines, which is the line is the scaling law, and the dot represents an empirical point that we had trained. Um, yeah, so, and then you could do the same experiment, but now you could look at validation losses when you're considering these same flop experiments while reducing the amount of unique data. And this validation loss for autoregressive is something like this, where as you see, as you're reducing the unique data, you're starting to see overfitting happening, where where if every curve is very divergent from one another. But in diffusion, we find that like all the curves looked very similar uh, for a meaningful amount of time, which also hints at this data reuse factor that I talked about.
Oh, okay. So, yeah. So, a follow-up question. So, every curve. Okay. So, let's say AR 100 epoch. So,
So this will
so
100 epoch will see 1% of unique data, but will be trained for 100 epochs.
Okay. Okay. And okay. So, so you're plotting the validation loss as the model is being trained for
Yeah,
100
exactly.
epochs.
Yeah.
Okay. Okay. It's not like every point is a differently trained model, like it
Yeah, yeah.
was in.
So
Okay.
only in
Cool.
this now every point is differently trained. In this is just validation loss, and every line is different.
Yeah, I was very confused when I first read the Muninghoff paper as well, because it was, I mean, confused not because it was not written properly, it was because like I'm not used to seeing such curves and experiments. So yeah, thanks for
And
clarifying.
this just explains like how much data repeat affects the training process, for instance. And then you can, because we have fitted scaling laws, you can
Oh,
find all
one so sorry, one very interesting so can we go back to the previous plot? Yeah, so on the right hand side, what we basically see is so having unique data doesn't really help with the validation loss as much, right? Like you
that
have
too.
so imagine you have a training corpus like like there are high quality and low quality data. So one can imagine like training an autoregressive model over your entire 1 trillion token, or someone else can just pick 20% high quality data and do 5 epochs of training and probably hope that like you're better off, like the diffusion will do a better job than the
Yeah,
autoregressive model.
yeah. So I mean, yeah. So these are some interesting things to study on what role does the high quality versus low quality. So you could do this, which would be very interesting. Consider like a
Mhm.
small proportion and train it for more versus train. Um,
Yes.
So I mean, we extrapolate these scaling trends using some and find some interesting statistics. So this is like a popular results from the Moninhoff paper, where they find for autoregressive, repeating until 4 epochs is as good as having new data. So here the dotted lines is using new data, unique data, and the solid line is when you repeat data. And if you see until 4 epochs, you get the same validation loss across different model sizes, which is across different flop settings. And for
What? So,
yeah,
Mihir, I'm so sorry, I'm interrupting
yeah,
you so
no,
much,
sorry. Yeah,
but
go ahead.
also like this is a very information dense plot. Okay, so we see every point here, right? So, and there's a subscript that says 1 epoch. So, how many tokens was it trained for? Like when you say that model was trained for 1 epoch, or was it? Is it like?
Yeah. So these plots are more like they're just scaling laws. So we fitted the scaling laws using all the prior results that we have, and in this we are just trying to extrapolate these scaling laws over unique and fixed unique data regime and multi-epoch settings. So this is not like a specific empirical point, but this is just extrapolated scaling laws using the fittings that we have found.
Oh, okay. I need I
So
need to
so
think
for
more.
instance,
Okay.
like for instance, we fitted these two equations, right? Like this equation and this equation. So this equation was
Oh,
for
sorry.
single.
I don't see. Okay, so there was some lag. Okay, so yes, this is the equation. I see the
Yeah, yeah.
equation now.
So basically there are two equations. One is this, and the second one is this. This is for multi-epoch settings, and this one is for single epoch settings. And then you fitted this, and you got a good enough R square, which is like basically you're able to explain a high amount of variance in your data. And now
Yes.
what we're doing is we are taking these equations and we are plotting them. Okay, just the equations that we have fitted using all these learned constants, and we are plotting them over here. And we are trying to see like, okay, until what point, until is there a specific epoch value until which the unique data and the repeated data get the same negative log likelihood. And interestingly, for autoregressive, it turns out it's still 4 epochs. Like the repeated scaling law, like the data repeated scaling law and the unique scaling law follow the same laws until 4 epochs.
Okay, okay, just so that I understand properly, so you have fitted this equation, and the quantity n is 200, let's say 217 million parameter, right? Okay, so
Yeah.
you've put n there, and okay, so sorry, your equation has n prime, which is like the total number of parameters and the number of training epochs. So you fix the size of the model n, and you vary the number of training epochs to get n prime. Okay, now you do the same for the D as well. Okay, my question is for D, like, do you fix the number of unique tokens or per epoch, or how
Yeah.
do you?
So the way we have done over here is like we try to be compute optimal. So let's say we with a certain, let's say we are considering this much amount of compute, we consider what is the like at different, so these things that you see 217 million, 425 million, 745 are at different flops. So we
Yes.
find what is the right number of parameters and right number of unique data for this,
Oh,
and,
okay, okay.
and then we assume
Oh,
uh,
okay, okay,
with
okay.
that, if we were doing repeating, then how would the curves look like?
I see. I see. I see. So, okay. So just so that I understand, you have the chinchilla law, which tells you for 217 million parameter, what is the optimal number of
Tokens.
tokens that you need. So you have n and d, and then you compute n prime and d prime by varying the number of epochs, and those, and that'll give you the number of training tokens on the x-axis as well. Okay. Okay. Good. Thank you. Thank you. No,
Yeah. So
I think I
these
had
started
misunderstood
one
the plot
solve with
initially when I
chinchilla,
saw
and
it.
then after that we repeat. Sorry, go ahead.
No, no, I think I had misunderstood the plot when I first read the paper. I had misunderstood the plot, but yeah, thanks for clarifying.
Yeah, and for diffusion, what we find is like until 100 epochs, you get the same validation log likelihood as the validation loss as the unique data setting. So basically, this is like a popular result from the Moninhoff paper where they found 4 epochs for autoregressor. We find for diffusion it's true for 100 epochs. So because of this, like all these like experiments, for instance, okay, should you take high quality data and train for 100 epochs versus train for like all these things become very interesting to study as a result of this. And these things are maybe future works or something. Um, yeah, pretty much what I said, which is 100 epochs for diffusion, 4 epochs for autoregressive. And then you can go and also, like, because you get better validation loss, it should also translate to better downstream results. So we consider some benchmarks, and this is the random baseline accuracy. And then autoregressive. So here, autoregressive is like with the best validation loss, which is after that point, it starts overfitting. It gets these results on downstream. And then we also added a baseline for autoregressive flop matched. So because diffusion is trained for much longer, we thought like maybe you can also have autoregressive with the same amount of training compute. And interestingly, you find that on some benchmarks, for instance, Hella Swag and Pika, even the overfitted models accuracy improves. Like 3 out of, let's say, 8, 9 benchmarks that we consider. On all other benchmarks, the accuracy actually reduced after the overfitting point. Uh, and for diffusion, still, if you compare against the flop matched or the best validation loss autoregressive, it's still most of the time it's better than all these baselines. And
Okay.
this is, yeah.
Sorry, one like what is the setup here? Like,
So this is like
how
with the
big is
100
the?
million unique data points that we had, we were training autoregressive and diffusion models for as many flops as we can.
I see.
And
I
then
see.
we
As
took
many
the
flops.
autoregressive with the best validation loss that was there in the contour plot, which is 144 million parameter trained for 50 epochs.
Mm.
And then we plotted it over here and you saw the accuracy. Then we also considered this flop matched because diffusion was trained for much longer compute, more compute. But this flop match will have like a lower validation loss, sorry, higher validation loss because it's overfitted. But accuracy on some benchmarks increases even after overfitting. And then this is diffusion, which is the best validation loss, which was 3.55 trained at 500 epochs with 400
And,
million parameter model.
oh, okay, okay. And then sorry, the AR column is for the best. Is for the AR checkpoint with the best validation loss.
Yeah. So there are
Okay.
two here we consider. One is with the best validation and one is with the same amount of training compute.
Yeah. Okay. Okay. Cool. Right.
Uh, and then you could like actually study, okay, is there like a interesting, because you find that there are across different unique data ratios, you find that, okay, there's a point always you find where diffusion starts to beat autoregressive. And then you can be like, okay, is there a point, like, can we analytically find where this point is? Because it seems to happen very commonly across different unique data settings. So this is like the difference between the diffusion loss and autoregressive loss as a function of the amount of compute you have, which is C, and U is the amount of unique data you have. And then you can equate this to 0 and you can be like, okay, is there like a compute for a given amount of unique data after which the loss becomes 0? Because when it becomes 0, after that point diffusion starts to beat autoregressive, and before that autoregressive is better. And we take all this, because we have fitted these scaling laws, we can actually solve these scaling laws and we can get an equation as to what is this C critical at which this delta loss is equal to 0. And we find it to be this interesting equation, which is very simple and log linear. And now in this equation, you can actually put in the amount of unique data you have. Let's say you have a billion unique data points, and you can get the amount of compute at which, after which diffusion will start to outperform autoregressive. And then basically we plot this histogram kind of a thing, sorry, heat map kind of a thing, where this red color, so here the x-axis is unique data, y-axis is the flops, and this red color is when you should actually use diffusion instead of autoregressive. Like if you have this much, like basically if you have more compute than data at this ratio, then you should start considering diffusion models as your primary modeling objective, because they will be able to extract more information from less data. And if you're in this setting where you have, let's say, more unique data but less compute flops, then autoregressive might be a better choice as per our empirical fitting. And because it's this line, we can also actually we try to see if this equation that we found also holds empirically. So we trained using higher data budgets like 500 million unique tokens, and we find that it somehow is nearby the line that we had predicted, and it's not entirely off. So the equation that we have fitted gives a rough estimate as to when, in terms of validation loss, diffusion might match autoregressive's performance. Um, so the conclusion is pretty like straightforward, which was we were thinking if you're compute bottleneck, like if you're, I mean, it's evident from the previous plot that if you're in this compute bottleneck setting, then autoregressive might be a better choice. And if your data bottleneck, then diffusion might be a better choice. And in some case, it makes sense also if you consider in the current foundation model settings, like the reason maybe why we are all using autoregressive could be because we are all compute bottleneck thus far. Like we have to spend money to buy compute, but data is pretty much free. It's available on the internet. So that's why maybe right now we are in compute bottleneck settings, but maybe in the future we will be in the data bottleneck settings. In robotics, this conclusion is even interesting because in robotics, there's this people who train in simulation and there are people who train in real world. So in simulation, because simulation is all because of compute, you might want to consider an autoregressive model. But in real world, you might want to train diffusion models. And we empirically also find this to be true. Like papers right now that are doing diffusions are usually doing real world training. So we released this paper in this, yeah.
Sorry, one follow-up question. So why do you say, there was a slide, okay, real world training. So sorry, what is real world training? Like when you have data from
yeah, so in robotics, for instance, you have to collect like teleoperated data using a human operator. And your data collection is actually, you have to use a human operator to collect specific trajectories in the real world data. So in that you have to, it's very costly to get data. Like you have to use a human operator's time to collect data. So you're actually bottlenecked using real data. In simulation, for instance, you train on the compute, you train on simulation environments, and you assume a sim to real transfer. So in those settings, you usually become compute bottleneck because simulation is a result of compute, but real world data is a result of humans going and collecting data for you.
Oh, so okay, so with real world data, because we have fewer data points.
Yeah,
that's
basically in real world data, you're bottlenecked by data. In simulation, you're just bottlenecked by compute. There's no like data. So we did release this paper in this format on Twitter, and we actually had like an interesting like Twitter fight or Twitter war, you can say, and it actually improved our paper. So I'll cover that too. Simo tweeted our paper saying, everyone get your top 1% quality data and train 100 epochs right now, which is I think also what Shubham said. And then Lucas co-tweeted it and said, AKA data augmentation. Not sure how you can write the whole paper and not once think of running AR with augmentation or dropout. So basically what he's suggesting is like we want to train AR with all these data augmentations like dropout, and we hadn't shown those results in the paper. And actually, like we had tried these experiments. We had tried before releasing, we had tried running augmentations on autoregressive like dropout and stuff like that, but they didn't work. So we thought of not reporting them in the paper because it didn't help us explain the results in our paper. So we gave a rebuttal to him, and pretty much I'll summarize the rebuttal, which is that the red line here is like the loss, the best diffusion loss that we have, which was 3.55, if you remember. And then this was the default autoregressive model, which we were considering. And then we tried dropping out the attention. And we also tried to do token masking, like dropping out random tokens in the sequence. But none of these seemed to help. And so basically, our point was that all these augmentations don't really help much in autoregressive training, and they don't help explain diffusion's loss function, for instance.
Oh, I have a quick question. So, like when you say attention drop, you mean you just do not, you introduce a bias in the attention matrix where a token does not attend randomly to a subset of the tokens, or
just like for instance, like for instance, when we are doing causal attention in autoregressive, we randomly pick some mappings in the causal attention and just switch them to be non-existence, for instance. It won't attend to it, and we randomly pick 50% of these. And then token drop would mean like you make sure it's fixed, so you never attend to that token across layers. In attention drop, you would just randomly, but the masking might be random over different layers.
Oh, I see.
So we rebutted him, and we told that I mean you could see why it won't, like just masking out random tokens shouldn't explain diffusion's ability, because diffusion is somehow like learning things using random orders, and like it's randomly, in a way, implicitly randomly factorizing this joint distribution, and which you can't enable by simply doing random masking in the token sequence, for instance. And then he suggested an interesting experiment to us, so which is highlighted over here, where what he says is like, why don't you train autoregressive, but at the beginning of training, so autoregressive is trained using only left to right order, but what if you also introduce other random orders in autoregressive training? So n is equal to 2 would mean you're doing left to right and you're doing another random order, so a random permutation, and n is equal to 3 would mean left to right with 2 other random permutation, and you fix this n, like the random orders you're considering, before you start the training. So you're doing, let's say, n-1 random, you pick n-1 before you start training, you pick some n-1 random permutation, you also consider left to right permutation, and then you train the model like this. And the assumption is that if this token ordering and random ordering is really important, then you should see the loss improving, validation loss improving as you're training for more epochs.
Okay, one follow-up question here. So, okay, so in this experiment, you have your AR model, and you do like left to right, like next token prediction, right? So you always do next token prediction, and on top you have some random ordering. And for when you do random ordering, like how do you do it? Like let's say, is it like you have, let's say, token 1 maps to token 5, which maps to token 3? Is it something like that, or?
Yeah, so the way we do it is like we take the standard left right order and we just add some noise to it. So then it becomes something like this. So for instance, let's say the standard left to right would be 0, 1, 2, 3, 4, 5, 6, 7. So here the sequence length is 7, for instance. So now we are creating, let's say, 15 different random combinations. So it will become 0, 2, 1, 3, 4, 5, 7, 6, 0, 4, 1, 2. So you'll just have these random permutations. But one important thing you're doing is you're still maintaining the positional embedding. So the model still knows that this is in the second location and this is in the first location. It's just the order in which it's predicting now is different. So it's first predicting the second token instead of first predicting the first token. And then you get these 15 random permutations as a result.
Oh, and then let's pick the very first permutation, right? 0, 2, 1, 3, 4, whatever. So there, sure, you have you have your tokens. You apply positional embeddings, shuffle them according to this order, and then the token 0 maps to token 2, and then the token 2 maps to token 1. Is that how you would? Okay.
Yeah. So basically, like you just do the standard next token prediction. So you use 0, 2 to predict 1, you use 0, 2, 1 to predict 3, and you're just making sure that the model knows that the 2 is at 2. And the way you would do it is, if you're doing absolute positional embeddings, you'll just add the absolute. If you're doing rope, then you will have to somehow encode it in your rotary positional embeddings that this is there. So you do it in the rope space. So he suggested this experiment, and we tried this out, and interestingly, it seems to pretty well explain like this ability of diffusion to be so sample efficient. So here the blue curve is the standard autoregressive, and then the red curve is diffusion. And if you noticed in the previous plot, like pretty much there's no improvement and everything was overfitting at the same point. But then we see with these plots that as we increase the value of n, we start seeing the best validation loss to reduce, or the validation loss to reduce. And we also see the overfitting point to keep going ahead, becoming 80 or becoming 100, for instance, and slowly starting to come closer to the diffusion's best validation loss, for instance. So there's a little bit of caveat here, which is that in the blue and the green one, we are using the left to right factorization in all these blue and green curves, we are using the left to right factorization. In the red one is still the negative elbow for diffusion. So that is one thing to note, but the important thing is that at least the green one keeps improving in the left to right validation log likelihood as you're adding all these random maskings.
This is very interesting and quite related to this esoteric language models paper that we have as well. My question here is that, so how do you decide? So, okay, you have two losses. No, wait, so given a training batch, how do you decide which permutation to apply?
Yeah,
Like,
so
is
we
it?
just randomly pick it. Yeah,
I see.
so we just randomly pick, and the interesting thing here is like the model itself has to figure out which permutation it is from the sequence.
Yeah.
Uh, so because we have not introduced an idea of target positional embeddings, the model
Yeah.
actually doesn't know which one it is, and it has to look at the sequence order and it has to predict. So if we increase the value of n to be very high, then it will become extremely difficult for the model to understand which sequence it is. So that's why at high values of n, it will become over regularized in a way. But we operate in these settings of n is equal to 16, where it's fine enough for the model to, let's say, estimate on which of the 16 it is, and then it uses that to predict the next token.
Mm. Oh, so basically the model doesn't know, let's say the permutation is 0, 1, 2. So the model doesn't really know that the token 0 maps to 1 or 20. It has like no
Yeah,
idea.
yeah,
You
yeah.
don't
No.
provide that information. I see.
Yeah, so but it will know once it sees sufficient amount of sequences or
I
sufficient
see.
amount of IDs in the sequence. So
I
let's
see.
say
I
after the
see.
fourth or fifth token, it will know, okay, it is this one, and then it'll use that to predict.
Oh, I guess like we have a question from Dilip. Like, hey, Dilip, like, do you wanna quickly?
Yeah, sorry. So is it for a part, but each model sees many different permutations, right? On a single training run, you see many different permutations. So it's, I guess I'm still wondering if, if so sometimes, 2 will follow 3, sometimes, 5 will follow 3. So how is this something then that the model would learn?
So like, I mean, so the assumption here is like, given we have maintained like n is equal to 16, which is a low enough n, the model, after seeing sufficient amount of IDs in the sequence, let's say after seeing the first 5 IDs, it would be able to classify as to, okay, out of these 16, it's this one. And once it's able to do that, then it'll use that to predict it. That would be the assumption. So that's why I was saying that you don't want to increase the n too high so that it becomes impossible to predict. Like there's just so many possibilities now.
I see.
So
And just, I think you said this, but just to clarify, you're not prompting it saying like predict the next token, and you know that the next token is the 5th token, right?
no, we're not doing that here. So we wanted to keep the autoregressive. So because this was mainly for explaining why. So we tried to keep the autoregressive model exactly the way it is without changing anything except the data. So we could have introduced a thing called target positional embeddings and done it the way RAR and all these Sigma GPT papers did it, but we did it specifically this way just to make sure it's. And we also actually tried a version with RAR, and we find the same to hold true with target positional embeddings. Like the same conclusion holds true even with target positional embeddings. We just reported this because it's much cleaner, and we are just
Thank you.
changing the data.
Thanks.
Yeah, so mainly like the interesting thing of this experiment is like token ordering explains diffusion sample efficiency. And what I also find exciting about this is like you could maybe interpolate between diffusion and autoregressive as a result of this. You could think of ways of doing that. And ideal thing to do is like you want to ride ideally the Pareto front of compute optimality and data optimality. And maybe something like this, a combination between this could allow you to potentially do that in the future, where you could, let's say, be so much compute efficient and so much sample efficient. Uh, and I would also like to highlight this paper that came out after us, which is Diffusion Language Models are Super Data Learners. And what is cool about their paper is that they scaled up to even bigger model sizes and data sizes. And they found that, so for instance, we our results were mainly up to like 500 million unique tokens. They scaled it up to a billion tokens, and they find that this holds true even at that point. And they primarily focus on downstream results, and they find on HelaSwag and MMLU, when you scale your unique data to 1 billion unique tokens, the red curve again here is diffusion. You start seeing diffusion starts to beat autoregressive in these settings after 80 epochs, let's say. So it is a good thing in a way that it validates our findings, and it also says that it holds true after above a certain number of, like it holds true on scale. So it might be like an exciting direction to explore in the future. Yeah, pretty much that concludes my presentation.
Right. Yeah. Thank you. Thank you so much for the great talk. Now, I think we're happy to take questions. Like.
Yeah. I mean, yeah. If.
Okay. We have a question from Dejan, and also from Orgus. So yeah, Dejan, like, would you like to unmute yourself and?
Yeah. Hi. Thank you for the talk. Yeah. So my question is, so this is only for masked diffusion, right?
Yeah.
Have you tried anything on like uniform diffusion and like, or maybe even continuous? Like how?
So
Are there
I
any
mean,
differences?
no, we haven't tried it so far. I overall like my. I mean, if I have to guess, I would think that for uniform diffusion, I'm not sure like why I'm not sure why for uniform I'm not sure why for uniform diffusion this might be better. Let's say I assume it will be equivalent, but I don't see a reason why it might be better. I think uniform diffusion in a way is like a little bit less compute optimal because you also have to learn this mapping of going from uniform to you have to first learn like okay that this is noisy, and then you have to also learn how do you map it to the clean signal. So you have to learn two things at once, and so I expect it to be less compute optimal. The good thing about uniform diffusion is like you can start like you don't have to you can for instance you can start at a random thing and you can just start denoising, so you don't really have to go to this mass token space. So editing and all these things become interesting in uniform diffusion because you can just take a random token and just don't do any masking and just start from any location. About continuous diffusion, I think I would expect this to hold true in continuous diffusion. I mean, there might be reasons to believe that continuous diffusion might be even more sample efficient than discrete diffusion, because they are doing everything in the continuous space and they are adding noise in the continuous space. So you're not just masking discrete tokens, you're masking some continuous concepts, for instance. So, but again, the issue with continuous diffusion is like it requires even more compute. So I think if you guys are aware of the Played paper, it showed that continuous diffusion requires 64 times more compute as autoregressive to match negative log likelihood, whereas for discrete mass diffusion it was 16 times. So I would expect more epochs and more compute. I mean, one more interesting finding is that if you look at the current continuous diffusion in image space, these models are usually trained for like 2000 epochs, like the state of the art models. We are discrete diffusion, we are still doing 500 epochs. So I think it somehow makes sense because like if this ratio is 4, if you need 4 times more compute, maybe you need 4 times more epoch, and maybe you start seeing more sample efficiency at the cost of more compute. So I don't know, I think both are exciting and both have their own trade-offs.
Okay, thank you.
Well, we have August with this question. Apologies if I'm butchering your name. Like sincere apologies, but yeah.
Oh, it's correct. Thanks.
Thank you.
Yeah, thanks for the talk. I remember these Twitter threads back when you released the paper. So this point of this token ordering, filling up much of this gap between diffusion and AR. Do you think there is some advantage internally to the diffusion architecture, like bidirectional attention or masking, or is it still just the token ordering, and is it essentially equivalent to the autoregression setting, just with more token orderings that serve as augmentations in a way?
I mean, like, I mean, I might be wrong. Maybe there are better people to answer this question. But the way I look at it is like, I think, like, the benefit of doing causal attention with this token ordering is that you have like you can do KV caching, you have high throughput, and so I see there's a lot of benefit of doing causal attention through this target positional embeddings. The benefit of maybe bidirectional attention is like you have lower latency, because you just have much more expressiveness, and yeah, it's a latency throughput trade-off. And I would I to my okay, if I have to guess, I don't know empirically, so if I have to guess, I would guess I think we want high throughput going forward. So I think doing causal attention with random token orderings with introducing some notion of target positional embedding should be good to go. Maybe Shubham can add something.
Yeah, so like, no, actually, it's a great question. Just that I understand. So your question was, so we have AR model with these permutations, and then we have this diffusion training, right? So was your question like which one is better, or like the advantages of each? Was that is that what you're asking, or?
Yeah, more like does the diffusion architecture bring anything, or is it mostly about the token ordering?
I mean,
Oh,
mainly like, it's like is the bidirectional attention critical?
Yeah, I mean, so in our recent paper, esoteric language models, it is essentially an any order autoregressive model where you train the model with random permutations. So Mihir's experiment, they restrict the number of permutations to 16. But imagine you are training, imagine you're training imagine you're training a language model where you have causal attention and all possible, and you're training the model on all possible permutations. Then essentially what you have is an esoteric language model, or SLMs, right? And it has amazing benefits. Like of course it's like it is a diffusion model at the end of the day. So you're applying this permutation. So it is very data efficient, like Mihir presented in his talk. And also because of this causal nature, you can do KV caching, and because it's diffusion, you can do parallel generation as well. So yeah, I mean, the takeaway is that, when you train a transformer with causal attention, with random, all possible random permutation, it unlocks this amazing properties in mass diffusion models that weren't available before, mainly KV caching. Yeah, mainly KV caching. Yeah. So yeah, and also you can compute exact likelihood of the models by exploiting the random permutations. So one of the questions a lot of people ask, right? Like you have this diffusion elbow, you have the exact likelihood for AR. How do you even compare those two numbers? In diffusion, you cannot compute the exact likelihood, but you can with this. You can exploit this random permutations to compute the exact likelihood. Sorry if I went off a bit tangent, but
no, that's fine. Can I ask one quick question more? So I guess these results are of sampling one token at a time. Can you comment a bit on is there any hope for parallel generation also achieving the same performance?
Oh, I think in Mihir's talk, everything was about likelihood, and we're computing the likelihood of the model. It doesn't capture the parallelism in the discrete diffusion models, right? So for that, you need other set of experiments. So I think in today's talk, we did not touch upon the experiments that highlight the benefits of parallel generation in discrete diffusion models.
Thanks.
Okay, then we have Dilip. Or yes, no, sorry, we have Albert. Sorry, my bad. Albert is next.
Hi, thanks for the nice presentation. I was still wondering about the overfitting in language modeling. I mean, I was wondering whether with better regularization you can reduce or get rid of the overfitting, and then you still might improve over what you see now. I mean, you discussed already about the reordering, and you discussed about attention dropout, and I mean, we also have the other dropout, weight decay, and I was wondering, maybe with some better, I would expect that you should always be able to overcome the overfitting in some way, and maybe we just need some better realization there.
Yeah, I mean, like you can think of this current idea as a form of regularization. Like this is a regularization in the loss function, where we are training using all these augmentations and you're getting benefits. And a lot of these regularization are sometimes very orthogonal to one another in the sense like for instance, the regularization you get from weight decay can't just be explained using regularization using a different loss function. So if you look at current state of the art, let's say models in on ImageNet, for example, like there are so many regularizations. You have data augmentation, which is a regularization in the loss function. Then you have regularization using weight decay, and you have other regularization also sometimes using ensembles and things like that. And I think a combination of these would be needed to become more sample efficient in terms of algorithms. And yeah, so they are quite independent, and we in this one we focus on the loss function, which is the diffusion objective, but you can get a lot of benefits too from weight regularization, ensembles, and all these other forms of regularizations. But I mean, these might be orthogonal. Like you can get the same ones also from diffusion models if you add weight regularization to diffusion, and if you add ensembles to diffusion, for instance.
Yeah. Okay. Yeah. I mean, maybe that's still maybe a question. So
Yeah,
I'm
so
not sure. Maybe
So
yeah.
maybe for
one thing I'd like to add here is, okay, at the end of the day, what do we want, right? So the gist of the talk was that you have diffusion. In diffusion, you apply some augmentations to the data, which is wiping out words and making the model predict the wiped out words. And that augmentation gives you two things. One is that it makes your model more data efficient. That is, when you have finite data, finite number of unique tokens, your model extracts more value from the data. And the second is parallel generation. The parallel generation, because diffusion models can generate multiple tokens at the same time. Now the experiment that we see on the screen, right? Like you have an AR model and then you just apply some permutations, let's say 15 different permutations to make it more data efficient. It is cool. It is a trick that makes your AR model more data efficient, sure, but it does not give you this advantage of predicting multiple words at the same time. Right. So that's the thing about diffusion, right? Like it's a very well principled way of approaching this problem of parallel generation and also like data efficiency. So yeah, just to share some thoughts from my side, but yeah.
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 I mean,
Yeah.
yeah, I mean, yeah, I mean, for your question for other ways of regularization, I mean, there are like some work studying this, and I feel like most of these things would be orthogonal to one another, and it's worth studying, but I would expect them to be orthogonal. Like there are many axes of generalizations.
Yes, yes. I mean, I was just wondering now when you had more weight decay or dropout or so, maybe then that or some other regularization, it might help then more for autoregressive models than for diffusion models. So and then in the extreme case when you make the model infinitely large, in the end you get the best performance, because right now it looks like from your graphs that diffusion models would scale better. But that's what I mean. I don't know the answer. Maybe there's just no way to get such the similar scaling trend for autoregressive models.
Yeah, I mean, yeah, like I do think like I think I do find like this regularization using diffusion objective has like some unique properties. I think maybe one way to think about it is like multitask learning. Like you're learning from just one task, which is left to right order, and you're just thinking in a specific way. And when you think in every possible order, you learn better causal dependencies about different concepts, and you're able to extract, like you're just extracting more information from a single data point, which seems unlikely that just weight regularization could achieve. Yeah.
Yeah, thanks for the answer.
Cool. Next we have Dilip, Rohit K. Dilip. If you wanna unmute yourself and yeah.
Yeah, thanks for that. I have a more general question, which I'm hoping folks who know more about this can broadly shed light on, which is in practical settings, how do you select? Because my impression is you pre-select the sequence length right before you run this, and so in practice, how do people do that?
I mean, at least in our thing, the way we did it is the sequence length is based on the maximum sequence length in the data set that we have. So
Yeah,
like,
I mean, in practice, when you look at models like LADA, right, that can do variable length generation, the way, okay, so you don't really need to fix your sequence length. What you do is for 1% of your training batches, you randomly sample a sequence length from, let's say, between 1 to the max sequence length, which is like 2048 or 4096, whatever, right? And just doing that makes your diffusion model robust to, like during inference time, you can select whatever sequence length and then do generation. The challenge is always that the same thing, right? Let's say you have a prompt and then you don't really know how long your response is going to be. Yeah. But after you've done this kind of training, during inference, you start with a good guess, let's say 128 tokens. You would do diffusion over 128 tokens, and then you move on to the next block of 128 tokens, something like block diffusion proposed, right? So the recipe is simple. Like you start with the MDLM model, corrupt your training with 1% of your training batches seeing smaller sequence lengths, and during inference you just shift to block diffusion. So yeah.
Yeah, and also like I mean, if you do the random order thing, then you have this flexible length thing because of the causal attention. So that
Oh yeah.
too is another
Yes.
benefit.
Yeah. That as well.
Sorry, can you clarify that point?
So
Like,
Mihir, take over.
Yeah, I mean, basically, if you do like Subham was talking about his esoteric language model. So if you do random order generation or any order autoregressive, because of causal attention, you can have a flexible sequence length in a way. Because the reason why your sequence length is fixed is because you're doing bidirectional attention.
Mm-hmm.
But once you have causal attention, you are allowed to generate as many tokens as you want.
Yeah. Okay. Great. Thanks.
Next we have Ridong. Again, apologies.
Thanks for having me.
Yeah.
Yeah. Great talk, Fox. I have a question following up his question. And that is basically, I'm thinking about if we want to do really long, ultra long context modeling, this is very common for today's large language models autoregressively, right? And if we want to do that, like for example, we're fine-tuning our diffusion language models into this ultra long context setting. Won't that be very inefficient? Because considering that you can, through just one forward and one backward, you can train the whole autoregressive sequence, but you need to train, multiple times for diffusion language models.
I didn't exactly follow the question. So is the question that maybe Shubham, did you?
Sorry,
yeah.
I was responding on chat. Sorry, could you repeat the question?
Yeah,
Yeah, of course. Yeah, so,
if you can
basically I'm thinking about that. If we're doing training on very ultra long sequences, so for example, 8 kilos, right? Like somewhere around this range, right?
Yeah.
And if we're doing that, for autoregressive models, we just need one forward and one backward, then we can train the whole sequence, right? But if we are doing it with diffusion language models, then if this n goes very long, then we need to train n times until that we can follow all the states of this whole diffusion process. So won't that be less and less efficient when the context is growing longer and longer?
Oh, okay. So your question is, as your context length increases, the diffusion training will be more expensive because you need to see that. Yeah. Yes, I guess. I don't have a good answer there. It will be more expensive. No questions asked. But I mean, I think yes, it will be more expensive. I mean, diffusion training is more expensive than autoregressive training, right? But our intuition says with longer context, like diffusion should be better, only because it has bidirectional attention for those reasons. But I don't really know if it's actually gonna how expensive the training is gonna be, or it's an empirical thing. So yeah, people need to run it and see. Yeah.
Yeah, I mean, also I'll add that with this. If you look at in this random order fashion, like if you're doing then your loss sits on pretty much every token, right? And you're not doing some random masking because you're randomizing the order. So maybe it could be that your compute becomes a lot more efficient because you're calculating loss on every token because you've randomly permuted the sequence now. So it could be that firstly, which is that random permutation could increase compute efficiency. It could also be, I think it's very I think maybe we think of, I mean, it's interesting to study this, and I don't have a very good answer, but we usually think that if the loss is sitting on every token, then you're actually using your compute more efficient. And it's not that clear because maybe there's a lot you're getting even through the visible tokens. Like if there are certain visible tokens and certain invisible tokens, even if you're learning from the invisible tokens, the visible tokens are also giving you something to learn from. So my point is I think it's even if your loss sits on less tokens, you're still learning maybe a lot, and you're learning a lot more than just simple left to right order. but you could also trade it off by doing random order or giving more importance to, let's say, left to right order, or something like that.
Yeah, I get it. That's a good question. Good answer. Yeah.
Yeah. All right. Cool. Thank you. And then next we have Joy. Joy Rachel. Joy, do you wanna unmute yourself and?
Yeah. So hello everyone. So I want to ask a question.
Yes.
There was a part where it showed the data splitting and the epoch. So I want to know why the data was splitted that way.
Sorry, could you repeat? We missed your voice.
I said there was a part you showed where you splitted the data with the epoch training. So I was trying to get some clarification on why it was done that way for the diffusion model.
Oh, no, so sorry. The first part. Your connection was a bit choppy.
Okay, I'm sorry.
No,
It's
data
splitting.
Oh, the data splitting. Okay. What about the data splitting?
Yeah, with the epoch training time. There was a part where it was 100%, and then the epoch time was 1. And then when it was 50, I think the epoch time was about 3. So I wanted to know the thought process behind it.
Oh, so you're saying with the data splitting, this epoch with 3 something, right? Like, I mean, like, can we go to that slide where you had you mentioned something about like the data splitting, and
this one?
Yeah. Yes.
I mean the main reasoning. I mean, I should actually put this as 25%, but the main reasoning behind this experiment was just to maintain the same number of flops. So when you do it like this way, which is like 5% data, 20 epochs, 10% data, 10 epochs. If you look at the multiplication of 25 into 4 or 50 into 2 and 100 into 1, you end up having the same flops. So we are just trying to see, like, if you maintain the same amount of compute but have less and less unique data, how do these trade-offs hold? And you can study the value of unique data as a result of this. So this shows that, let's say, when you have this data fraction, while you're using the same number of flops, which is compute, but you just have less unique data, then what is the decay rate? So you can study decay rates using this way of like maintaining the same flops while having different proportion of unique data, if that answers your question.
Okay.
Yeah, I mean, basically, let's say you have data with 100 million tokens. Now, how do you can do many interesting things with it, right? Like you can train a model for 1 epoch on the 100 million tokens, or someone else can take 50 million tokens and train it for 2 epochs, or someone else can take 10 million tokens and train it for 10 epochs, right? So yeah, so in Mihir's paper, he basically studies this behavior as to like, yeah, there are like very, very advantages and disadvantages associated with each of the splits. And in the next slide, he sort of like does an analysis as to, like what happens when you do this sort of training. So yeah.
Okay. Also, was it data trained like from scratch or it was fine-tuned?
Oh, this is from scratch. All these experiments are from scratch.
Okay.
Right.
Thank you.
Yeah.
Thank you.
Yeah. Right. Okay. I guess there are no other questions.
Okay, awesome.
Releasing. Okay. So so Gilad is asking, are you gonna release your models on Hugging Face?
I think they are released on Hugging Face already.
Oh, they are? Okay, cool.
Yeah. So yeah, if you follow the code, like I think they're either on Hugging Face or they're just some Google Drive link, but I think most likely they're on Hugging Face.
Okay, they should be able to find you if they read your paper, right? Cool.
Okay.
All right, cool. Cool. Thank you so much, Mihir, for this wonderful talk, and thank you
Thanks
so
for
much.
arranging and organizing this. It's pretty.
Of course, yeah, of course. But yeah, thank you so much for coming by, and I'll see you next week on Monday.
Thank you. All right.
Bye.
See you.
Bye.
Bye.